Good afternoon, everyone. I'm Ryan Allen.
I'm Cruze Cameron.
I'm Abby Stewart. And I'm Shelby Pollock.
Today we're going to talk a little bit about the phylogeny and the evolution of the turtles. And
Okay.
Cruze is going to kind of set the stage for that.
Okay, so to get us started, the initial ancestor that is assumed to exist before our first discussed species is hypothesized to have been a reptilian tetrapod without a shell. These don't have a shell. This has a shell. The first apparent physical change that seems to initiate the evolution of turtle shell is the broadening of the ribs. Once the ribs are broadened, the next identified transitional characteristic is the beginning of a belly shell. Once the belly shell is created, the next fundamental characteristic is the fusion of the belly shell and the top outer shell.
So, first organism on our phylogenetic tree is called Milleretta. It is a recognizable reptile. It's kind of like the first one out of turtles in that it's not actually considered a stem turtle, but it's the first organism that really shows any turtle-like characteristics. So in our video here, you can kind of see just kind of the ribs and how they look kind of rounded. And that would have been like the normal reptile, the tetrapod-like style that she was talking about. As you can see here, this is what Milleretta's skeleton would have looked like. And that's what an artist's depiction of what Milleretta itself would have looked like. Some derived characteristics we can kind of talk about with it are it did have broadened ribs, but they were L-shaped instead of T-shaped, which is significant all throughout the turtle phylogeny. Milleretta also has paired gastrula, and basically what paired gastrula are they're kind of the beginnings of a belly shell. They're these little bone-like structures kind of on the underside of reptiles. And so those two things are probably the most significant things that we see in Milleretta. The next transitional form is the Eunotosaurus, as you're about to see here. The skeletal structure of a Eunotosaurus is really significant in that it has broadened ribs. So it's kind of the first stem turtle that we've seen in the fossil record. It lived about 260 million years ago. Its fossil was found in South Africa. It has several defining characteristics. One of them is it has 9 dorsal vertebrae instead of 10, which was very common for reptiles at the time. And each of those 9 vertebrae were significantly longer to compensate for having 9 instead of 10. Off of each of those vertebrae, you had these broadened ribs, and broadened ribs really allowed for the kind of the beginning of the formation of the carapace. So in relation to how you make a shell, obviously broadening ribs, like a tree said, is the first step in the process. So it's really significant to see in the stem turtle that we have these broadening of the ribs. We also have paired gastrula in Eunotosaurus, which plays a big role in the second part of forming a shell. One other interesting thing to note about Eunotosaurus is a lot of turtle shell or turtle phylogeny research is really recent. So Eunotosaurus has been known about for a while, but it was always debated as to whether or not it actually was related to turtles now. And until 2013, there was no real evidence to support or refute the fact that it was. But in 2013, one of our fossils of Dactycheles that you can see on, that we're going to talk about a little bit later, was discovered. And then in 2015, June of this past year, Papacheles was actually discovered. Papacheles is so recent it's not even in this video. And those really kind of solidified Eunotosaurus's relationship to turtle phylogeny.
Okay, so after the Eunotosaurus, the Papacheles was found. The Papacheles was a groundbreaking discovery because, as he said, Papacheles was literally the last one discovered, but it's so important. It's up here, in the middle of the whole phylogeny. So that was a really groundbreaking find because it tied together these previous species to the ones that we have modern day. The Papacheles species is categorized by its lizard-like body shape and the presence of rod-like bones that appear to be fused together in the underbelly of the lizard. The discovery of the Papacheles confirms that the belly portion of the turtle shell, called the plastron, formed through the fusion of these rod-like rib structures and its shoulder girdle.
I didn't put a video last time. I forgot Papachelis was not in this video.
Okay, so the next transitional species is the Odontochelys, and this was just recently found in 2013 in China, and it was one of the fossils that confirmed the dinosaurs as a stem turtle. As you can see from the video, it had a complete belly shell, which was the most significant thing about this species, and it's like it's in the second step of making a shell, so it's really close to being a turtle. Other characteristics of this fossil, instead of the belly shell, are it had a broadened neural spine, axial rest of the ribs, a loss of ventral ribs, and the sternum. The clavicle and the interclavicle had become incorporated into the plastron, which is the belly shell of the turtle, and it also had partial teeth.
Okay, so the final species on our poster is the Cruze, and it was the first recognizable turtle. It was found in both Germany and in Thailand. It's 214 million years old. It actually is the oldest fully developed turtle ancestor found, and it kind of ties everything together. This organism has the underbelly, the top shell, along with all the other developed characteristics of the previous ancestors. For example, it has a short tail, fully developed carapax, and no teeth, just like the common modern day turtle.
So now we've talked a little bit about the transitional forms of turtles. You kind of got an idea of how that looks. So now we want to talk about a little bit about how the turtle, or some hypotheses as to how the turtle's shell formed. There are basically two hypotheses. The first one is called the composite model. And basically what the composite model says is that the turtle shell formed through the fusion of osteoderms. And for those of you who don't know, osteoderms are bone-like structures or bony structures on the back of many reptiles. For example, a crocodile or an alligator now, those little bumps that run all the way along their back, those are all osteoderms. And so basically scientists advocated, or paleontologists advocated, that the turtle shell formed through the fusion of these structures. So the other hypothesis was is called the de novo model. And basically what it says is that's not what happened. The turtle shell evolved through a different process, most likely overgrowth and outgrowth of the ribs. But for a long time, neither hypothesis had a lot of support in order to determine which one really happened due to a gap in the fossil record. And then in 2013, when Odontochelys was found, it kind of solidified the fact that the de novo model was probably the more correct model due to Odontochelys' lack of osteoderms. And then in 2015, when Papachelis was found, it also kind of solidified the idea of the transitional form of broadening ribs and then formation of the belly shell and then outgrowth of the top ribs. Another line of evidence that kind of supports the de novo model is the BMP gene. And basically what BMP stands for is bone morphogenic protein. And that's present in modern day turtles. And it is expressed a lot in the embryo or in embryonic development. Basically, it causes the bones to overgrow, which is necessary whenever you're kind of making your shell or your house completely out of bone. So those are kinds of the evidence that really support the de novo model of how the turtle got its shell.
Okay, so we talked a lot about the phylogenetic ties and how the turtle developed the shell. But I want to talk a little bit more about why scientists hypothesize that this happened and state some selective pressures that scientists can hypothesize. The first and most obvious hypothesis is that the change from shellless to having a shell came about simply for protection. While we all know that turtles can hide in their shells for protection, few people know the main hypothesis for why, well, one of the main hypotheses for why they have the underbelly. And some theories say that the underbelly shell was to protect semi-aquatic turtles from predators that could be swimming underneath them at all times. Turtles are obviously not the quickest or the most fierce out there, so they had to develop some sort of mechanism to keep them safe from the constant predation and constant predators looking for food. tying into protections, turtles use their shells as shelter, and the shell could have quite possibly been selected for due to extreme climate and weather changes in that time period. This adaptation could very likely have kept them from freezing or drying out in their shells because of heat. We know now that some very, very few variations of turtles can actually like completely close their shell to keep out outside variables, so that's pretty cool. Another hypothesis is that turtles' shell is to control buoyancy in the water and to help them move throughout the water better. Obviously, none of these are 100% because nobody can tell exactly why the turtle created the shell, but they're just hypotheses. So.
Okay, so since the Bermuda-Chellis turtles have diversified tremendously, they first divided into two suborders, which differ in the way that they pull their necks into or under their shells. Pleurodira are known as side neck turtles because they fold their neck sideways along the body under the shell's margin, unlike the turtles in Cryptodira, which lower their necks and pull the head straight back into their skull. Pleurodira is further divided into three different families. The first are made up of freshwater turtles, known as African side neck turtles. The second are aquatic turtles, commonly known as South American river turtles. And the third are Austro-South American side neck turtles. Cryptodira is further divided into four superfamilies: Testonoidea, Chirosternoidea, Chelonoidea, and Trianchia. Testonoidea contain pond, river, and marsh turtles, as well as tortoises. And tortoises differ from normal turtles because they're larger and they're solely land-dwelling. Chirosternoidea contains small mud and musk turtles. Chelonoidea contain the living sea turtles today, like the loggerhead and the green sea turtles, and they live only in the water and they aren't able to retract their heads into their body. And Trianchia are pig-nosed turtles and soft-shell turtles, which differ from normal turtles because their shells lack horny scutes or scales, and so their shells instead are leathery and pliable, which allows them to move more easily in the water and on land. In addition to those four superfamilies, Cryptodira contains the big-headed turtle, the snapping turtle, and the alligator snapping turtle, which are known for their long necks and powerful jaws.
A summary of our phylogenetic tree. We would say that turtles originally derived from Milleretta Unitosaurus. And what modern day turtles derive from these species are the broadened ribs. And just to set the scene for what this time period was like, they lived 260 million years ago, and that was during the Permian time period. And this time period is characterized by extinctions amongst lots of different reptiles and small mammals that lived during that time. And this is believed to have inhibited the evolutionary development of these because obviously predator-prey relationships change, so they would have to find different ways to protect themselves. The last three studied organisms, these three, lived during the Triassic time period. This time period was also characterized by extinctions, but the extinctions of dinosaurs. So these were before dinosaurs, these were after dinosaurs. And they were also around when cone-bearing and gymnosperm plants began to develop. So just to wrap up, these are we learned that we have broadened ribs, we have the development of underbelly ribs and the development of an underbelly shell, and then the development shells fuse together and create a whole belly shell. And then towards the end, when we get to Providentiales, we have the completed form belly shell and the completed top shell. So in addition of these anatomical transitions giving us an idea of how all of these turtles are related interspecies wise, we can also conclude that make conclusions based off these anatomical species about what their closest living relative is today. So we would hypothesize that there are hypotheses that the modern day turtle is related to the modern day lizard and snake, and that's because these ancient turtles have a diapsis skull, and this means that they have these two cavities behind the eye sockets. And so since these ancient turtles had the diapsis skull and modern day snakes and lizards have a diapsis skull, we can like conclude that they're related somehow. I think it's interesting to mention that although ancient turtles had a diapsis skull, modern day turtles do not have diapsis skulls, but they have anapsis skulls, which means that they don't have these cavities. So like that's interesting because the diapsis skull is like obviously like a better evolutionary characteristic because it allows movement of the neck and shoulder and like full like head rotation if needed. So it's just like interesting that they would have a diapsis skull, which is better, but then evolved to not have an anapsis skull.
So that's pretty much the phylogenetics and turtles. Questions?
Questions? Oh, yay.
All right, so most modern turtles have at least some connection to water. Did you turn up any evidence in your research as to how water dependent the ancestors were?
We know they were terrestrial. We don't know whether or not they were semi-aquatic or strictly terrestrial, but we know they came
But
from lizards.
I think maybe like I didn't like research this, like I'm just like making this up. But
Gotta love
like
honesty, right?
because the time period that these existed, there were like lots of different extinctions of like modern or like organisms that were like around at that time. So like maybe like since like predator-prey relationships changed, like obviously like maybe they moved towards water like as time went on.
That was kind of an hypothesis whenever we one of the articles that talked about Papacheles mentioned bone ballast, and so just like Cruze said, all this kind of speculation. If they were predators, and if they were like water-faring predators, but they lived and nested on the land, it could have helped them swim. It could have given them protection from anything that would have tried to eat them from below. Just
It could have been like kind of like reversal of like our whale tail, like how whales are like on land and then they like went to water and like could kind of be the same
because
scenario.
these are also very small, like only a couple of inches long. So they're not.
Wait.
Yeah, they're not
That
big
is
at all.
like the-
Like I know, I'm not sure about these two off the top of my head, but I know
Population.
Papacheles was only about that long, from head to tail. Right, that long.
And they have like
They had a long
more
tail.
tail than body.
That's a good question. Other questions? So I'll ask my question. So let's talk about these broad ribs. I want to just know, like, thinking about this, do you have to have a full shell in terms of maybe having protection from predators? When you think about why even having broadened ribs might be selected for?
I mean,
Well, we talked about this yesterday, and I don't know if you want me to give the answer that you gave, but we talked about how the broadened ribs makes you wider, obviously, and less not as narrow, so you couldn't be swallowed or eaten as easily. But
Just kind of thinking
More
about that,
solid.
like why those broadened ribs might have been selected for, right? Even before you get the full shell, that maybe that would keep you from being eaten by some predator,
yeah.
kind of like the stickleback fish with their spines. Just like-
I guess going back to the whole like block thing, and like you said with the stickleback thing, like the broad ribs would give you protection, but not if a shark came and ripped your skin off.
Right.
So like if you had just bone there and the shark bit you but like couldn't chew you up, then it might just spit you out and you could go on your way. So that could be selective pressure. There was a lot of studies. I know at least two of them that basically just don't know. There's not a lot of.
I was gonna say, what do you think the most challenging part of this for you guys has been?
definitely the lack of information. I mean, there's not a lot.
There's really not a lot of why.
Yeah.
There's a pretty good amount of how. There's a pretty good amount of transitional forms, but there's not a lot of, I guess, ultimate questions.
I mean, we definitely know less about this than any of the other transitions. So, I mean, just the fact that you guys highlighted this, that so many of these fossils are just now kind of coming to light in the last like 2 years or so.
So weird.
Yeah,
I would think
yeah,
we could
so-
learn more about it.
I think you did a great job because we have very little information. Good work. Any other questions? Let them off the hook. right, good job.